which will represent the approximation or the smooth version of the original image. But in the outer region will be the high frequency component, which will represent the details, okay? The fine details of the original image. Now, based on this, then you will know, for this case here, the casting surface, the roughness is 12 μm, but the lower one is very rough. The surface roughness is 280, okay? So this will show you a lot of fine detail, right? So the corresponding, see that? This is the corresponding Fourier spectrum. This is 3D perspective. So you can see that it's wider, okay? It's straight. It's wider, okay, compared to the rough surface here. It's more concentrated around the DC term, right? Why is that? Because this one, it shows a lot of fine details. You mean you need more frequency component to represent the local detail information. But for the very rough surface, most of it, you don't need, most of the frequency component is black, means it's very close to zero, because we don't need that information. Okay, we don't need that information so that the frequency component is concentrated, okay, just around the center. Next. If we go back to the original image here, one of the reasons, for image compression, maybe you can learn a JPEG standard, a lot of difference. A lot of it is based on Fourier transform, which means what? You need only a very few non-zero frequency component, then you go for the inverse Fourier transform, then you can recover the original image. That's it. That's why we can use Fourier for image or signal compression. 影像压缩了。This could be just 1K, but this could be 1K by 1K image, but however, you may need only about just 1% of the frequency component. So you can transfer from one place to another place, not the whole image, but just few data point, and you do the inverse Fourier, and you can recover the image. That's one the other reason why we a lot of standard is based on the Fourier, okay, Fourier transform. Because when you see the black means what? It contains no information. Most of the frequency component equal to zero. You don't need to send zero, right? Or store zero for anything, okay? So we can use this property to identify it's a very fine roughness surface or a very coarse machine surface, casting surface. Okay, so that's it. Because it shows no direction, so you will see the frequency component everywhere. Okay, everywhere around the center. Okay, circular around the center. Okay. So I try to list with some paper. You could have more than 28 frequency features, but just summarize some of it. Okay, for your own application, maybe you can design your own features from the Fourier, okay, Fourier spectrum here. Okay, the first one, you pick up, you just find the energy in the major peak. As I mentioned, this cannot, we will exclude the one in the center. Okay, don't use the one, because no matter what image you have, the one in the center or the so-called DC turn will have the maximum power. So U1V1 is the maximum, but excluding the DC turn. Okay, then you convert it into 100. You don't need to time 100, but it just in the original paper it converted into a percentage. Okay. And second is Laplacian. Why it called Laplacian? When you take a look, you will know. Do you remember when we talk about the age detection, the Laplacian? This is a Laplacian, right? Laplacian operator. It's exactly the Laplacian. See that? Okay? In the four neighbor. This is the one in the middle, okay, here. But anyways, U1V1, which means first you take the major peak, and you find its neighbor, okay? You find its neighbor. So by looking at this, you will know the difference for, I'm not going to back, okay, for, see that? The neighbor will be quite different, see that? Okay, not mention the one here. Okay, for the structural texture, the neighbor, the Laplacian will be. For this one, you may not see. You can see only the power spectrum in the horizontal line, but not vertical line here. Okay, so it suggests a lot of things to do. Okay, so then you can look for the Laplacian for the second peak. I need to say it's symmetric. For this one, if you find the major peak here, don't find the corresponding one as the second peak. As I say, they are symmetric. Okay, they are exactly the same. You must watch out. Okay, black. Okay, and find the spread of the major peak. It just try to find the number of adjacent neighbor that where always neighbor also have a large power. Okay, it's up to you. For this case, you just use a half, okay, or something. Okay, and you can define your own neighbor. And this is what I'm saying, the frequency. Okay, you want if the center is 0, 0. This will be the frequency. It represents the frequency, PD, okay, of the original signal. Okay, this is the frequency, and this is the relative orientation for the major and secondary peak. Okay, then we take the arctangent for the major peak is the secondary peak. Okay, so for structural texture, this will be what? 0 degree, and there's no the secondary peak will be the same as the major peak, right? So the difference will be 0, but it won't be the same for the random texture. Okay, here. Okay, so it can show you. Okay, and a lot of the other one is so isotropic. Actually, this equation, whenever you take a look of this equation, this is calculate the variance of U, variance of V, covariance of U and V. So what can you do here? Remember what you have done. Now forget the Fourier. In the original image, you calculate x squared, y squared, xy squared. This is what? Where did you run it? And you can use this to form the covariance matrix. And once you have the covariance matrix, you can calculate the eigenvalue, lambda 1 and lambda 2. Remember, we talked about the car license plate for the schooner's normalization? Can you remember what I'm saying? 哎，给我编句子哈，不要看我，老师不笔试什么都忘了，那没有用。我跟你讲，那回去我都白讲，这个是在重复同样的事情。Don't you remember when we talk about how to rotate the license plate? You calculate the variance, right? The variance x, the variance y, the covariance x and y, and the covariance y and x are actually at the same. Then once you have this one, you can calculate lambda 1 and lambda 2. Right. Now let me ask. If we take the ratio lambda 2 over lambda 1, what will be the value? The value? This value should be very close to. Suppose lambda 2 is less than lambda 1. This value, this measure should be for the structure, for the spectrum like this. Lambda 1 and lambda 2 well, should be very close to what? And what about this? What about this? For the lambda 1, the lambda 1 is very large. For this one, lambda 2 should be very close to what? What? Say it. For this one, what should be the value for lambda 2? You know, eigenvector 1 should be orthogonal with respect to eigenvector 2. Lambda 1 represents the variance in the major x. Lambda 2 is the variance. So for this one, the lambda 2 should be very close to what? The lambda 1 is wrong. What about lambda 2? 你都没有我期末考我就考，我跟你讲，都不回应我就考期末考，我就笔试了。If don't respond to my question, you will have written exam and include the final project. Okay? You have to do your study. When I ask you what will be the lambda 2? 0. Should be very close to 0, right? So just based on this, you will know the image will be a structural texture or a statistical random texture. Okay, just by looking at this value. What about the ratio here for this one? Lambda 1 and lambda 2 should be very close to each other because there's no specific direction. It should be the same. So for this case here, the lambda 2 over lambda 1, the ratio must be very close to 1. So just by measure this value, you will know the original image is a structural texture or statistical texture. Okay? So okay, I will skip some of the details. Everything is based on lambda 1, lambda 2. Okay, just based on lambda 1 and lambda 1 based on here. I just put a note here. Okay. I keep saying this, right? It's based on the car license plate. When I talk about the Harris corner detection, they all based on the covariance matrix. Then again here, okay. Although it's based on the Fourier spectrum, but the idea are the same. Then you can use simply just based on U1 or V1 or the secondary peak U2, V2, and so on. Okay, and the distance. Okay, a lot of basically there. Okay, here what I'm just mentioned here. Okay. The other way around is. For the Fourier spectrum, we divide it into 4 quotients. Okay. We just measure the first quotient, the second quotient, third quotient, okay? But for some case, I mean, as I mentioned, they could be symmetric. If you look for 1, you may not have to look for 2. They are symmetric, they could symmetric, okay? 好，它把它拆成4个象限 right here. Okay, everything is larger than 0. Okay, if we put center, okay, the d theta in the center, it will be the quotient, okay? The quadrant 1 第一象限. Then you can look for the energy. You just look for the and okay, U plus V and times the the normalized power spectrum. Okay, quadrant 2, quadrant 3 and 4. Okay, but remember, if they are symmetric, don't look for both. They will be the same. Okay, the other for this one, for relative entropy, we can divide it into 4 regions. Actually, we should look for R1, R2, R3, and R4. Okay, circular, but the computational efficiency, we just simply take the square. It is much easier. Okay, when you have to run your own code, okay, it's much easier. So anyway, divide it into R1, R2, R3, and R4, and you can measure the power or the entropy. Okay, so again, this is for statistical texture right here. Okay, see that? I mean, for this case, the R1 could be large, but R2 and R3 will be very close to 0, right? But for this one, R1 is large, R2 could be also very large. And you can see some magnitude for R3 also, okay? So it depends on the corresponding or the original image is a fine texture or a rough texture, okay? Then it will tell you a lot of story, okay? So that's it. They are not all, okay? I mean, you can design more, okay? Just more than 28, but there are some very popular, okay, features that you can select, okay? And the good thing, let me say it one more time, they are not affected by random noise, okay? That's the good thing when you calculate. When you calculate the feature, for example, based on concurrence matrix, I mean, it could be affected by random noise, and the result, the feature value could be varied, okay, with a large variance. But when you go for the Fourier transform, basically the value will be very stable, okay, it will be very stable. It won't be affected by the random noise, okay? Okay, the last thing, today I may not have time to talk about the deep learning, but anyway, definitely I will end everything about the traditional machine vision today. Okay, the last thing I would like to talk about it because it's nothing to do with the neural network, but you can think of it as something to do with the neural network trying to run. Okay, now. Let me talk about the Gabor transform because it's extended from. Let me show. Take a look the note here. Okay. Let me show you an example. If I have an image, okay, a machine surface like this. Okay, if this f of x, y. I convert it into a Fourier transform, okay? You know, it will distribute it like this one, right? I mean, this means the bright point. Everyone agree with me, right? Right, okay. Now, if I have some red scratch on the surface, what would happen in the corresponding Fourier spectrum? What would happen for this one? You will see a very light I mean, they must be orthogonal with respect to each other. 它们一定要正交。And you will see a line. Why is a line? Because there's only one single scratch. It's not repeated, no frequency at all. So you will see a very light line here. But from here, do you know where is the location in the original image? No, there's no way you will know that because Fourier transform is a global representation. There's no way you can know where is the location of the square. From here, you know something wrong, something different, but you don't know where is the location. Now, here's how you solve the problem. Next, the example is use a one-dimensional, okay? You use a one-dimensional case. So this is the input, okay? A continuous signal, for example. And this is the, again, okay, J is a complex number. Now, this inverse is not important. Here, this is a so-called short-time Fourier transform. Everything is the same here, but it times a window. See that? The W. You put, okay, this is because we are talking about time series. It's the same, just like the image, but with times a window, a small window, which means you can think of tau as the shift of the window function. Okay, so if you have an original signal like this, suppose you have something wrong, then we move the window, you move the window, okay? One time step along. Then you calculate the Fourier transform. So in that case, you will know where is the defect or anomaly. That's the idea. We times a time window, okay? A time window. Okay, tau is the shift. So you can think of the image, in the image here, we shift the window, okay? Pixel by pixel. So in that case, you may find something wrong for the scratch. That's the idea. That's the so-called the short time. We don't look for the entire period. Instead of we look for the short time period. Okay, that's the idea. Just W here with times a window. Now, if the time window, I mean, it is a logical, a reasonable selection, we select a Gaussian time window. We use, it does not have to be, right? It can be a top hat. Okay. If we use a Gaussian time window, then the short time Fourier transform is called Gabor transform. That's it. Okay. So Gabor transform is a short time Fourier transform. Which means you need to define what? The filter. You need to define the filter. 就是你要设计滤波器。You need to define the filter. First, you need to determine what should be the window size, okay? And what should be the shift. You can shift 1 pixel at a time or 2 pixels, it's up to your application. Okay, but anyway, if the time window is a Gaussian, then the short time Fourier transform is called Gabor transform. Now we can go back to talk about the Gabor transform. For the user, you need to specify the frequency and orientation. Okay, just specify. So if you have no idea about the orientation, now again, you just assume the orientation could be 0, 45, 90, 135. Okay, 180 degrees and so on. Okay, which means you need to design a lot of filters. 你要设计很多滤波器. Okay. Each one will represent different orientation. The other one will represent the frequency or the scale. Okay, there's a theory. It says that's how our human see the world based on just like the couple transform. I don't know. I don't know if it's true or not. I cannot tell. But anyway, here is the couple transform. Okay, J again is a complex number -1 square root. Okay, and G, as I mentioned, is the window function, and we take a Gaussian. Okay, then we take a Gaussian function. Okay, so again, XY. So you can design your own filter. Okay, for this case here, the filter is fine. It's 5 by 5. The one in the middle will have the XY to be 0, okay? And the one here will be -1, 0, and so on. So once this is given, so for the user, you need to determine what should be the bandwidth, okay? The bandwidth. You know, if the bandwidth is very large, you can get a more smoothing surface. Okay, so that's it. And for the user, you need to think of what should be the frequency, what should be the orientation. So when you apply Gaussian filter, you need to do the convolution with a lot of filters. 你说每个你就是要设计滤波器，这个滤波器呢，你就要让它来做炫技运算。所以呢 ，for example, if you have a 5 frequency and 5 orientation, which means you need to use up to 25 filters. When we talk about deep learning next week, the filters are run automatically by the model with some training sample and a given objective, which is called loss function. But if we go for the Gaussian filter, this is the only thing you need to do here. Just design the Gaussian transform with, but for the user, you need to specify what should be the bandwidth and what are the frequency and the orientation you are going to look for. Okay, so that's it. So in the early day, as I mentioned, in the early day of the deep learning development, a lot of research love to compare the filter run by deep learning and with the Gaussian transform. That's one of the reasons. But anyway, again, because Gaussian transform is a complex number, so it can calculate the real part and the imaginary part. Okay, here is the Gaussian. Again, for the real part, it's a cosine function. Okay, xy. That's why again, in the middle have the coordinate 0, 0, and all others will be just +1, -1. Okay, and the imaginary part is the sine function. But for the user, you need to specify what should be the orientation and what should be the frequency. Now remember, these two are the filter. They are the filter. 它是滤波器了。我讲它是滤波什么意思？你把这些纸带进去，这个滤波器就出来了。Okay, I mean they are the filter. Once it defines the bandwidth sigma and the frequency and orientation, then all the corresponding elements value in the filter they are determined. Okay, so that's it. Okay, they are the filter. As I mentioned, even I didn't show the filter in such as 5 by 5, but they are. This is for the real part. This is for the imaginary part. That's it. The filter. Okay. Okay. So that's it. And so once you design the filter for a given filter with a given frequency and orientation, and you do the convolution with the image and move it pixel by pixel. Okay, slide the window. Then you do the convolution. Then you can get the real part and imaginary part. And from here, you can design your own texture features, okay? For example, you can simply just calculate the square of the real part plus the square of the imaginary part. And this might, if this value is very large, it means what? This image contains this very specific frequency and this very specific orientation. Okay, just look for the one with a maximum energy. Then you will find what should be the corresponding frequency and the orientation. That's how we design the Gabor filter. Okay? So that's it. Okay, as I mentioned here, just try to find the maximum. Then we use phi star, sigma star as the features that can be used to describe the texture feature. Okay? So if you have no idea at all, you just try out these 4 directions, which means at least you need 4 filters. Okay? And with different wavelengths. Here give some subjection, okay? This frequency, and that corresponding to the wavelengths of 16A42. But some prefer to use square root 2, blah, 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 okay? But let me give you the example here, okay? This one, you use a 4x8 Gabor filter. It means you use 4 scales with 8 direction, okay? Let me show you the last one, okay? See that? It will show you the filter in different direction, right? This in the vertical direction, right? Then you rotate clockwise, counterclockwise. And this is rotate clockwise, okay? And it has shown 4 scales, right? From the very fine scale to a very rough scale. So for this case, you will use up to 32 filters. 也就是它这里面呢用了32个滤波器. Okay, and then later on, you can do the convolution for every one of the 32 filters and find the one or some that will have a maximum response. Then you will know what should be the texture in the image. Okay, what should be the frequency, what should be the direction, okay? So that's the idea. That's the filter. That's the filter. And then let's take one more example. Okay, here's an image of a car or jeep. Okay, then you use 5 scales and 8 direction, which means what? You use up to 40 filter. Okay, 5个 scale, 8个方向. The direction will be the same as the above. Okay, but you use a 5 scale. Then we do the convolution. Okay, for each one of the 40 filter, then we do the convolution. Well, in deep learning, it's called what? The feature map. Okay, for each filter, when you after the convolution, then you will get the feature map. The feature map will represent what? With Gabor transform, then you will indicate the specific scale and the specific orientation. Okay, right? But when you use Gabor filter, we don't need to any optimization. You just design the filter. Okay, but usually for this case, you need to use up to 40. Then we do the convolution pixel by pixel in the original image, and here's the result. Okay, again, it just shows the filter. Okay, with different degree, with different scales. Okay, it will show you all. See that in a very rough. Okay, and show the different scale. Then we do the convolution with the original image, with the vehicle. See that in a fine scale, you can see it will show different. Okay, different details. Okay. Then in a very rough, see that? it just shows some of the approximation, okay, of the object in the image. So that's how it learned. We designed the filter, but later on, Carl, I don't have the time to talk about the deep learning at all today, but just show them how to use collab, okay? Okay, and also the Hopf transform, right? Carl, 他在这里Carl here, he will show you the Hopf transform we talked about last week. No assignment today, okay? No assignment. Don't worry about it, okay? And also, because I don't have a time to talk about the deep learning, but Carl will show you how to install the collab. But if you have the GPU in your lab, you can just use your own, okay? But I encourage you to just use the collab, okay? In case you don't have the GPU, and some of for your assignment, the deep learning model example, Carl's provided can be run on collab, but it may not executable in your PC because different version. You might have a different version installed in it, so it's up to you. Okay, but I still encourage you to try to install the collab. Okay, to make sure all the demonstrated example provided by Carl can be run. Okay, on collab and do your homework. Okay, so that's it. And don't forget next week I need the outline for your project. Okay, so that's it for today. Okay, okay, Carl. Okay, any questions before I go? So bring the deep learning part next week. Okay, I will talk about the CNN and net and then autoencoders. Okay. Okay, so that's it, and see you next week.
今天开始要做那个人构筑库。先做什么？书报啊，书报，书报还但我上的时候。 这个动物看起来比较难，但我是我那个这个我们还没有他的 experience 是学过的，所以比较慢，比较慢。但主要就是主要的概念，他们在我都会跟你讲，是一些可能在一些 detail 或是一些什么重点。我要就是重点我要学的，就那个部分不学这就算了，但是学的话要一点。可以就看一下。要吧？不是要什么那个后。 而且还有那个新的 version， 就是可能我们还没知道。如果是一个新的，就是 VJJ， 我们都知道，可能有新的分级 ，VID 也可能知道。明天会少一个人吗？少一个人。 不知道，书报应该是不会吧？不是实验室的。那你应该回去看东西在不在？没事，每个礼拜二他没在。
Okay, I will teach you how to use the Hopf transform for lines because there are two Hopf transforms, one for circles and one for lines. But I will only teach you how to use the one for lines. Okay. So for this we need the same libraries as usual. I'm going to demonstrate with wafer. You image. You can see it works. So we need first we need to open our image in gray level. A gray level image, not as a color one. Okay. First step. Then we need an edge detection. It can be sobels or canny edge. However, you must be careful when using the host transform because it requires the image to be thresholded. That means if you are going to use sobel operator that gives you the gradient and not the thresholded image, you need to do the threshold before using host transform. But because I'm using canny edge detection, it gives you the thresholded image, right? I should know. Okay. Then we just call the host lines, which is the method, and it will give you the lines. It accepts several parameters. The first one is the thresholded edge map. The second one is the resolution for the angle, for the pixel. So for this, we're going to use always one. The resolution for the angle, which is 1 degree, pi over 180 is 1 degree. And then we have the most important argument, which is the threshold. This threshold means the number of lines that intersect to be considered a single line. So that means if we put a lower number here, we are going to have more lines, right? Because that means we need less number of intersections to be considered a line. If we put a bigger number, a larger number, then we will have as a result less lines. Okay? Basically, the only parameter you need to consider is this threshold. Okay? And then we just call it, and it will give us the lines. However, the lines are not are in polar coordinates. That means they will give you a radius and an angle, not x, y. So you need to convert those values into Cartesian coordinates. Okay. So the first part of each line is the radius, and the second one is the angle. So we need to convert from polar to Cartesian coordinates, and then we can just plot those lines. Simple. As you can see, we have. Professor wanted for the assignment. It is not that good because you can see some lines here, right? I mean, you have a lot of lines here, a lot of lines here. So there's too many things you can do after this. For example, you can remove lines that are too close to each other within some distance. For example, 5 pixels. I don't know. You can remove lines that are not horizontal or not vertical, because obviously you need to have the angle. By the way, the angle is given in radians, not in degrees. Okay. So, got it. Okay. So basically, this is it. And from here, you can do a lot of things. You separate the die, for example, or anything. Questions with this? And, straightforward. So just remember that the image has to be an edge map, not a gray scale image, so you need to perform thresholding if you are going to use sobel's operator. But in this case it's canny, so it's already thresholded. So that's it. Now for the Google Collaboratory, it's kind of easy. You just need this collab.research.google.com. That's it. It's a Jupyter notebook. It has everything installed. You don't need to install anything. For these assignments, I have no idea which lab you are on, okay? So I have no idea which hardware, how you have your computer set up. I have no idea. So for this, I will recommend that for deep learning, you go for the assignments with this. Because I'm not going to explain how to install deep learning packages, because sadly, most of the packages now, they run better in Linux computers. I use Linux, okay? So I know how it works, but I know most of you will use Windows, so I have no idea how to install them on Windows. And I won't explain. So better stick to Collab for the assignments, because everything is going to be run in Collab. And it's quite good hardware, I would say. And it's free. You can run anything from CPU you're going to run, most likely I will repeat this again next time when we have assignment. If you want to run GPU, you just have to go to runtime. Then you have to go to change runtime type, and you have to select the GPU option because otherwise you are going to run CPU. Yeah, so that's it basically. You have to select GPU if you are going to run GPU because this is free. If you stop working, it will close the session. So you will have to be working all. Don't leave something running and then just go away because it will close the runtime and then you will lose everything you have done. It's not like the computer because it's a shared computer. So that's the only thing that you must be careful. Especially when you're running on GPU, I think it gives you like 30 minutes of inactivity. Question?
No.